Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. So here we're going to talk about the problem of the day 24. In a quadrilateral, the angles formed by the lines passing through the midpoints of one set of opposite edges and two diagonals are equal. Prove that the length of two diagonals are equal. So basically, we find a quadrilateral first, right? Let's call it A, B, C, D here. And we find the opposite edges, midpoint of the opposite edges. So for example, here and here, let's call it M, N. And we connect the diagonals. And we connect MN. What we learn here is that the angle formed by this line, the lines that are passing through the midpoint of the opposite edge, and the diagonal, right? This angle and this angle are the same. So let's call it PQ, for example. Then the angle AQM equals to angle DPN. And now we want to, that's a problem set. And we want to prove that AC equals to BD, right? We want to prove the length of two diagonals are equal. So for this kind of problem, the first thing we notice here is that we have the midpoint, right? And we also know two angles are equal. So we have to have this mindset that since we already have two angles are equal, which means we already have an isosceles triangle. And we want to prove that BD equals to AC. So we have to figure out a way that use this isosceles triangle. Okay, so we have two solutions. I'll talk about two solutions here. Two solutions here. The first one would be, let's think about the midpoint. Right, we have midpoint here, that's for the segment AB, and we have midpoint here, that's for the segment DC. And the easy thing is that if we want to prove that BD equals to AC, we just need to find the midpoint here. Let's call it point E, okay? If we connect ME and connect EN, we know that in triangle ABD, M and E are the midpoint of AB and AD. So ME equals to half of BD, and also ME is in parallel with BD, right? And similarly, in the triangle ADC, E is the midpoint of AD, N is the midpoint of DC. So EN is in parallel and equals to half of AC, right? And because ME is in parallel with BD, that means angle EMN equals to angle DPN, which equals to angle AQM, which equals to this angle equals to this one, right? Because EN is in parallel with AC. So it equals to angle ENM, which make EM equals to En, which means BD equals to AC. Okay, that's the first solution. And the second solution, as I said, we can think about this isosceles triangle. We want to use it, so we can force the BD and AC to form a triangle. So that means we can simply do a parallel line from D to AC, right? The AC parallel line from D and make this, let's call it DF. Make DF equals to AC and connect CF, connect BF, right? That means DF is in parallel and equals to AC, which make ADFC a parallelogram, which means if we connect DC and if we connect AF, the DC and AF bisect each other, right? So if we connect, and this bisector, this intersection point is a midpoint of DC, which is point N, right? Then we can see that in the triangle ABF, MN is in parallel with BF, right? Because N is a midpoint of AF, M is a midpoint of AB, so MN is in parallel with BF, and it's half of the BF, right? So MN is in parallel with BF, and we already know that AC is in parallel with DF, which means that the angle DFB equals to angle AQM. And because MN is in parallel with BF, that makes the angle DPN equals to angle DBF, which means triangle DBF is similar to triangle, let's call it ZPQ, which is an isosceles triangle, which means BD equals to DF. And because ADFC is a parallelogram, that makes DF equals to AC, which means BD equals to AC, right? Obviously, the second solution is more complex than the first solution, but that's the idea, right? Even though it's more complex, it's a very solid solution that you can derive step by step, because you want to prove that you already have an isosceles triangle. You want to prove two segments are equal. You can put them into a triangle and try to prove it's still an isosceles triangle based on the problem set, right? Okay, it's a problem of 1990 Russia Math Olympiad. I think it's probably for the 8th or 9th grade, not for the high school students. Okay, I hope you like this video. See you in next one. Thank you.